Assalamualaikum warahmatullahi wabarakatuh. So this is the lesson for three-phase rectifier under topic chapter 1, chapter 2 rectifiers. So this is the three-phase uncontrolled rectifier circuit where the power device are the diode, and as you can see we have a three-phase source connected in star, so VAN, VBN, and VCN, and we have three leg here. So all the upper group of the diode is numbered as a E odd number, while the lower group of the diode is numbered as an even number. So D1, D3, D5, D4, D6, and D2, and connected with a load. Okay, and we consider this load as a resistor. And this is actually the output. Okay, the output of the load when it is, this one is actually a resistor load. As you can see, it's almost DC current. And we also will noted that this is the voltage output of the three-phase rectifier, so it is also almost DC voltage. So that's why for rectifier, most of the AC to DC conversion mostly done in three-phase system instead of three-phase system, because the output is already considered a DC current and DC voltage without any filtering. Okay, so as can you see here, this is actually a voltage source. Okay, this is the magnitude VAN, VBN, and VCN, where these are a balanced voltage source, and each source has a phasor difference of 120 degrees. For a full cycle, for example, like this, for a full cycle, VAN, for example, here, VAN till this one. So please, you can see that the number of pulses at the output side can be this one, 1, 2, 3, 4, 5, and 6. Okay, so all together for one cycle we have what, 6 pulses. Okay, 6 pulses for the V out for one cycle of voltage source. Okay, so that's why sometimes this type of rectifier is called 6-pulse rectifier. So how to actually know which one is which diode will turn on and which diode will turn off? Okay, so it's actually depend on the circuit condition, whether the diode is forward bias or reverse bias. So the concept is same with the single phase diode, where the diode will turn on when the anode is much positive compared to the cathode. So for example, at this instant, okay, at this instant, so to know which diode at the upper group will turn on and which diode in the lower group will turn on, we look at the polarity, the positiveness of the source. Okay, so for this instant here, okay, we will see that, okay, so the VAN is more positive compared to the VBN and also VCN. Okay, so meaning that the diode, the anode, where the diode is connected to the phaser of A will turn on. Okay, so meaning that D1 will turn on. Okay, because VAN right now is the most positive compared to VB and VC. And for the to determine which type of diode will turn on, okay, so we need to look at which cathode of the diode that connected to the most negative, okay, value. So from here, for this instance, the most negative is VB and voltage. So meaning that D6 will turn on. So meaning that for this pulse, the first pulse, D1 and D6 will turn on. And then let's look at the second pulse here. Second pulse. So for the second pulse, we will see that the VAN still the positive. So meaning that D1 will remain on, while for the negative, for the lower group of the diode, so we look at we can see that the VCN is the most negative value. So VCN is D2. So meaning that for the second pulse, D1 and D2 will turn on. Okay, so that is how we determine which diode turn on. Okay, so since it has 6 pulse for one cycle, which is 360 degrees, meaning that one pulse here is actually 60 degrees because 360 over 6. Okay, so 60 degrees for each pulse. So from that, we can actually compute the voltage average output. So the voltage average output, so we can integrate from pi over 3 to 2 pi over 3, which is a 60 degrees here, and integrate with the Vm line to line sine omega t. So we will get the formula of the voltage output voltage, which is, as you can see, is at 3 times of the single phase values. And this is when you deal with the inductive load. So same with the single phase. So if the inductive load, if the L, omega L is much larger compared to the resistor, you will have the current to be almost a DC current like this one. And this is, as you can see, this is the diode. So this is actually current for resistive load. Okay, and this is the current output for the highly inductive load. So there's a difference where you can see that the current is actually a DC current. So that is one is actually the same application, same concept with the single phase rectifier. So we have some examples for you to do some exercise. And this is the three-phase control rectifier. So we are using the SCR to control the firing angle. So this one, the objective of using control rectifier is that we have variable voltage output and variable current output. Okay, and as you can see here, this is the angle 30 degrees. So when we have a 30 degrees angle, so you will have the output voltage to be like this. Okay, and if you have a 60 degrees, the output voltage should be this part. Okay, and if you have 90 degrees, you will have only this part. Okay, so as if you increase the delay angle, you will see that the voltage output average will become much smaller. Okay, and if you increase further to over than 90 degrees, you will see that the output voltage will become a negative voltage. And this is actually the equations that relate with the control rectifier. So we have 3 multiplied with V max line to line over pi multiplied with the cos of the firing angle. And same with the three-phase uncontrolled rectifier. So if your load is actually inductive load, so depending on the value of the inductor, so the output can become a DC current, so on. And we have also example 2, and also the solution for example 2, which is I leave it to you to discuss and to explore on the solution, which is actually the same principle that we applied for the single phase. So thank you very much for three-phase. So we have finished already on chapter 2, the rectifier, and we will go for the application of the rectifier in controlling the DC motor. Thank you very much.